Hello, my name is Joseph Kelleher, and I chose to do my project on statistical thermodynamics of thermalized electronic densities, in particular, connecting canonical ensemble theory to finite temperature quantum densities. So my project aims to connect CHEM214 canonical ensemble ideas, especially Boltzmann weighting and the partition function, to how quantum electronic densities change at finite temperature. I show this in simple model systems like the particle in a box and the harmonic oscillator, and then connect that same logic to how electronic structure codes implement finite temperature occupations. Thank you, and I hope you enjoyed this presentation. Motivation. Why do finite temperature densities matter? At 0 Kelvin, a quantum system occupies only its ground state. However, essentially all real materials and molecules exist at finite temperature. Once the temperature is above 0, excited quantum states begin to populate with non-zero probability. Which states are occupied and by how much is not arbitrary, though. It is dictated directly by statistical thermodynamics. In the terms of the language from the course, this comes from the canonical ensemble. Each quantum state is occupied with a Boltzmann weight proportional to the exponential of the minus beta times the energy of that state, meaning that higher energy states become accessible as temperature increases. Because of this, the electronic density is no longer the density of a single eigenstate. Instead, it becomes a thermal average over many quantum states, where each state contributes accordingly to its statistical probability. That idea is what's being illustrated in these two diagrams. The energy level diagram shows that real quantum systems have excited states available, and the Fermi-Dirac plot shows how occupations smoothly change with energy at finite temperature, rather than being a sharp step at 0 Kelvin. This concept is central to finite temperature electronic structure methods, warm dense matter, and behavior of semiconductors and metals at operating temperatures. It's also crucial for the numerical stability and physical correctness of modern DFT codes that use Fermi-Dirac occupations. The key takeaway from this slide is that once temperature is non-zero, electronic density becomes an ensembled average quantity, not a single state property. Statistical mechanics, canonical ensemble refresh, or NVT. Before we can talk about thermalized quantum densities, we need the statistical mechanics framework that underlies everything in this project. All of my results are based on the canonical ensemble, which describes a system with fixed particle number and volume that is in contact with a large heat bath at a fixed temperature. In this ensemble, the system continuously exchanges energy with the reservoir, but the temperature is held constant. That physical situation is what's shown in this diagram. The small box represents our quantum system, and the surrounding region represents the heat bath, with energy flowing in and out. The key result of the canonical ensemble is the Boltzmann distribution. The probability of the system occupying a microstate with a particular energy is given by the exponential of minus beta times that energy divided by the partition function. The partition function itself is the sum of those exponential energy weights over all possible microstates, and it ensures proper normalization of the probabilities. All of the temperature dependence enters through the parameter beta, which is equal to 1 divided by Boltzmann's constant times the temperature. As the temperature increases, the Boltzmann factor becomes less steep, and higher energy states contribute more significantly. Because of this, any observable that we care about, such as position, momentum, or electronic density, is no longer associated with a single state. Instead, it becomes an ensemble average, meaning we sum the observable over all microstates, weighted by their Boltzmann probabilities. This is exactly what leads to thermalized electronic densities. At finite temperature, the system samples multiple quantum eigenstates, and the density reflects that weighted mixture rather than a single ground state wave function. This canonical ensemble picture is the physical foundation behind finite temperature electronic structure methods, including the Fermi-Dirac occupations used in Octopus. Statistical mechanics, the connection to quantum mechanics. Now that we've reviewed the canonical ensemble, we can connect it directly to quantum mechanics. In a quantum system, the microstates of statistical mechanics correspond to the energy eigenstates of the Hamiltonian. These are the solutions to the quantum mechanical eigenvalue equation, where the Hamiltonian operator acting on an eigenstate produces that state's energy times the same eigenstate. So at a finite temperature, the system is no longer confined to a single eigenstate. Instead, it occupies a statistical mixture of eigenstates, where each state is populated with a probability given by the exponential of minus beta times the energy of that state, divided by the partition function, exactly as dictated by the canonical ensemble. This naturally leads to the thermal density matrix, which is defined as the exponential of minus beta times the Hamiltonian operator, divided by the partition function. The thermal density matrix is the fundamental object used to describe quantum systems at the finite temperature. From this density matrix, we obtain the finite temperature electronic density by summing the probability density of each quantum eigenstate, weighted by its thermal occupation probability. This expression is central to my project, as it shows that electronic density at finite temperature is an ensemble average over quantum eigenstates, rather than the density of a single wave function. The diagram on this slide illustrates this idea visually. Each horizontal line represents a quantum energy eigenstate. At zero temperature, shown on the left, only the ground state is occupied, so the system is in a pure quantum state. As soon as the temperature rises above zero, higher energy eigenstates begin to populate according to their Boltzmann weights, as shown in the middle panel. At even higher temperatures, more eigenstates contribute, producing a fully thermal mixture shown on the right. This mixed state behavior is exactly what the thermal density matrix describes, and it is the mechanism behind Fermi smearing, finite temperature density, functional theory, and the thermalized densities computed in Octopus. Thermalized electronic density. Now that we've established how quantum systems become thermal mixtures at finite temperature, we can focus on the key quantity in this project, the thermalized electronic density. So at 0 Kelvin, the electronic density is simply the ground state density, because the system occupies only its lowest energy eigenstate. At finite temperature, however, the system occupies multiple quantum eigenstates simultaneously. As a result, the electronic density is no longer associated with a single wave function. Instead, it is given by a thermal ensemble average, where the electronic density at a given position is obtained by summing the probability density of each quantum eigenstate, weighted by that state's occupation probability. These occupation probabilities come directly from statistical mechanics through Boltzmann or Fermi-Dirac statistics, and they depend explicitly on temperature and energy. As the temperature increases then, higher energy states become increasingly populated. This causes the electronic density to spread out, become smoother, and lose fine spatial structure that is present at 0 temperature. The figure on this slide illustrates this behavior by showing how excited state populations grow as temperature increases. Once the thermal energy becomes comparable to the spacing between energy levels, excited states contribute significantly. This ensemble average density is the central object studied in finite temperature electronic structure theory, and provides the foundation for the model calculations that I will show you. Fermi-Dirac occupation factors. Because we are working with electrons, the occupation probabilities we use are not simple Boltzmann factors, but instead follow Fermi-Dirac statistics. The Fermi-Dirac distribution gives the probability that an electronic energy level or CHEM orbital is occupied at a given temperature. Specifically, the occupation probability is given by 1 divided by the exponential of beta times the energy of the state minus the chemical potential plus 1. At 0 temperature, this distribution reduces to a sharp step function. All states below the chemical potential are fully occupied, and all states above it are empty. At finite temperature, that sharp step becomes smeared. States near the chemical potential acquire partial occupancy, and excited states begin to contribute with non-zero weights. This smearing of occupation numbers is a direct consequence of the canonical ensemble applied to fermions, and it plays a central role in finite temperature electronic structure theory. When we compute thermalized electronic densities, each wave function is weighted by these Fermi-Dirac occupation factors. As the temperature increases, more states contribute, which drives the broadening and smoothening of the electronic density. In practice, this is how finite temperature density functional theory and electronic structure codes implement thermal effects. Temperature enters through the Fermi-Dirac occupations, which then determines the ensemble average density. So the Fermi-Dirac distribution provides the direct link between temperature and electronic occupations, and the thermalized densities that I will show next. Example System 1, Particle in a Box. To demonstrate how thermalized electronic densities behave in a concrete way, the first system I consider is the particle in a box. This is an ideal starting point because it is a simple quantum system with known analytical solutions. The energy eigenfunctions are sign functions, and the corresponding energy levels increase quadratically with the quantum number. Because the spectrum grows with the square of the quantum number, higher energy states are separated by increasingly large gaps. And as a result, excited states only begin to contribute significantly once the temperature is high enough that their statistical weights are non-negligible. Using these eigenfunctions, the finite temperature electronic density is given by a sum over quantum states, where the probability density of each eigenfunction is weighed by its Fermi-Dirac occupation factor. Here, the occupation numbers are the Fermi-Dirac factors we discussed earlier. At low temperature, the density closely resembles the ground state density, which is peaked at the center of the box. As the temperature increases, excited states contribute more strongly and the density becomes flatter and more uniform across the box. This system is especially useful because it provides a clean test case. We can directly compare the expected analytical behavior with the numerically computed thermalized densities, making it an ideal way to build intuition before moving on to more complex systems. Particle in a box, density versus temperature plots. Here I show the particle in a box electronic density as a function of position for 4 separate temperatures. These plots illustrate the qualitative temperature dependence predicted by the canonical ensemble. At 0 temperature, shown in the blue, the density is entirely determined by the ground state, and as a result is a strong maximum at the center of the box and reflects the shape of the lowest eigenfunction. At intermediate temperatures, in the middle, a small number of excited states become thermally populated. These higher energy eigenfunctions have additional nodes, so when they are averaged together with the ground state, the density begins to flatten and lose some of its central peak. At high temperatures, shown in the red at the bottom, many eigenstates contribute with comparable weight. The density becomes much smoother and approaches a nearly uniform distribution across the box. This behavior is a direct consequence of the canonical ensemble. As temperature increases, more quantum states become thermally accessible, and the electronic density reflects an ensemble average over all of them. In the high temperature limit, the density approaches the classical expectation of uniform probability, illustrating the crossover from quantum-dominated behavior to thermally dominated behavior. Example System 2, Quantum Harmonic Oscillator. The second model system I consider is the quantum harmonic oscillator. Unlike the particle in a box, which is confined by hard walls, the harmonic oscillator confines the particle through a smooth quadratic potential. The potential has the form of 1/2 times the mass times the square of the angular frequency times position squared, and the corresponding energy eigenvalues are given by Planck's constant times the angular frequency multiplied by the quantum number plus 1/2. A key difference from the particle in a box is that the harmonic oscillator has equally spaced energy levels. The spacing between adjacent states does not increase with quantum number, which makes this system particularly well suited for studying thermal population effects. As before, the finite temperature electronic density is obtained by summing the probability density of each eigenstate, weighted by its Fermi-Dirac occupation factor. At low temperatures, the density closely resembles the ground state Gaussian. As the temperature increases, however, higher excited states become thermally populated, causing the density to broaden while remaining centered about the origin. This behavior contrasts with the particle in a box, where increasing temperature leads towards a nearly uniform density. The harmonic oscillator, therefore, provides a complementary test case for understanding how finite temperature ensemble averaging depends on the underlying energy spectrum. Harmonic oscillator, thermal densities. This figure shows the harmonic oscillator potential along with several of its energy eigenfunctions. Each curve represents a single quantum state, and as the quantum number increases, the corresponding wave functions extend farther from the center of the quadratic potential. At 0 temperature, only the ground state is occupied, so the electronic density is a narrow Gaussian centered at the minimum of the potential. As the temperature increases, higher energy eigenstates become thermally populated according to their Fermi-Dirac occupation factors. Because these excited states have broader spatial extent, their contributions cause the overall density to widen. The finite temperature electronic density is therefore not associated with a single eigenstate, but is instead an ensemble average over many quantum states, where each state's probability density is weighted by its Fermi-Dirac occupation. Unlike the particle in a box, the confining quadratic potential prevents the density from becoming uniform. Instead, the density broadens symmetrically while remaining centered around the minimum of the potential. This makes the harmonic oscillator a clean benchmark system for studying thermalized electronic densities and illustrates how the underlying potential shapes the finite temperature behavior. Ensemble averages and observables. At finite temperature, quantum mechanical observables are no longer determined by a single eigenstate. Instead, they are defined as ensemble averages over many quantum states. In the canonical ensemble, the thermal expectation value of any observable is given by a weighted sum over eigenstates, where the weights are the Fermi-Dirac occupation factors. This means that the quantities such as the total energy, position moments, and especially the electronic density are not properties of individual wave functions but of the ensemble as a whole. The thermalized densities I showed in the previous slides are a direct illustration of this idea. Each density is not a single probability distribution but a sum of many eigenstate densities, with each one weighted by how strongly that state is occupied at a given temperature. Importantly, all temperature dependence enters exclusively through the occupation factors as a function of temperature. The eigenfunctions themselves do not change, only how strongly each contributes to the ensemble. This ensemble-based viewpoint is central to finite temperature density functional theory, where the fundamental quantities are ensemble average densities and observables, rather than purely ground state properties. How electronic structure codes use ensemble averages. Everything I've discussed so far is implemented directly in modern electronic structure codes. Rather than working with a single occupied state, these codes solve for a set of single particle eigenstates and then assign temperature-dependent occupations using the Fermi-Dirac distribution. Once the occupations are determined, physical quantities, such as the electronic density, total energy, and forces, are computed as ensemble averages over those states. In practice, though, this procedure is often referred to as Fermi smearing. The key point is that temperature enters the calculation only through the occupation factors, while the underlying quantum states themselves remain unchanged. This is exactly the mechanism used in real space density functional theory codes like Octopus, which allows us to study thermalized electronic densities in simple controlled model systems before moving on to more realistic materials. Summary of key thermodynamic connections. To summarize the key thermodynamic connections, finite temperature and quantum systems is naturally described using the canonical ensemble, where the system exchanges energy with a heat bath. In quantum mechanics, this means that physical observables are no longer associated with a single eigenstate. Instead, they are ensemble averages over many quantum states. The electronic density, which has been the focus of this presentation, is therefore a thermalized quantity obtained by summing over eigenstate densities weighted by their Fermi-Dirac occupations. In electronic structure calculations, this framework is implemented through Fermi smearing, which allows temperature effects to be incorporated without modifying the underlying Hamiltonian. These ideas form the foundation of finite temperature density functional theory and motivate the use of simple model systems, such as the particle in a box and the harmonic oscillator, to build intuition for thermalized electronic behavior. With these connections in place, I'll finish by briefly discussing why this perspective is so useful and where it can be extended. Final thoughts. To conclude, finite temperature introduces fundamentally new physics into quantum systems by requiring an ensemble description rather than a single state picture. Through simple model systems like the particle in a box and the quantum harmonic oscillator, we can clearly see how temperature modifies electronic densities through state occupations. These examples highlight that thermal effects enter through ensemble averaging, while the underlying quantum structure remains unchanged. This framework is central to finite temperature density functional theory and provides the conceptual foundation for how electronic structure codes such as Octopus treat thermalized electronic behavior. And overall, studying thermalized densities in simple quantum systems offers valuable intuition for understanding finite temperature effects in more complex electronic systems. Thank you for your time, and here are my references. Thank you for listening. Thank you for your time, sorry.